Please welcome a program manager from DARPA's Information Innovation Office, Dr. Hava Siegelmann.
Thank you. So AI has great promise, and as a researcher in the field, I also know that it has some deficiencies. So my name is Hava Siegelmann. I'm on leave from the University of Massachusetts, where I'm a professor both in the computer science and in neuroscience. And I joined DARPA so that I can be part of this revolution where we make AI a better partner. So we see these great successes in AI. They play unbelievably games, they recognize images, but we always look at the success and are very happy about them. But when we take AI to be embedded in our own world, it's a little bit different. So if we think about Tesla self-driving cars or Alexa at home or Amazon, there are great successes, but there are also some failures. It seems as if AI is very successful in structured environments, but when I go to unstructured environment, it's more haphazard. And depending on the situations, these failures can be more or less costly. There seems to be one particular underlying reason that seems to be perhaps the reason to many or most of these failures. And this is the following. State-of-the-art AI, or as we call it machine learning, is given a program to follow and a training set to learn from in advance. It learns, and then it stops learning. Once it stops learning, it starts operating. So it can really do everything that we told it in advance. Kind of like a regular computer program. So you have a computer program, and it does what it does, and it never learns over its lifetime. So in this sense, AI is not that smart because everything that it learned was from the data set that it was given to it in advance. Now, you would agree with me that you cannot think of every eventuality when you prepare a training set. So at some point, you'll have input that you don't know what to do with, and the system will fail. And especially when we're talking about AI that we put today everywhere in our lives, and we have AI that works in more complex environment, AI starts talking to other AI, it seems like we're getting closer to more possible failure modes. So we can think about it in this graph, where the X is time and the Y is performance. So during the training time, the performance go up, then they remain constant until you reach some input that has changed, that is not exactly what we know to do. At this situation, the machine learning will not be able to do something else. They will just repeat and repeat their own answer. What we would like to do is to have machine learning that has this capability to go like the green line, in the sense that it will be able, during its life, to continue and improve, so that when it looks back, it will say, at the end of the training phase, I was not that expert. Now I am. And that's why we created the program L2M, or Lifelong Learning Machine. This is a large program. We have 17 performers and 9 smaller groups. And together we try to solve it. So we're actually working very much together. We run it a little bit like a research lab where people talk to each other and support each other's effort. What I would like to do is to show you some of the successes we currently have. The program is 10 months into the program, so we're not yet to the first year, but we already have some successes. So the successes I would like to tell you are all coming within terms of the pillars of what we call the pillars of lifelong learning. The first of them is continual learning. Continual learning is the ability to learn more as you see more inputs. This is a basic in human intelligence. It was never the case in AI until now. The second pillar is internal exploration. In internal exploration, you don't get a new input. You kind of look at what you had, at your experience. You try to better understand it. You reorganize what you had, and you get ready to prepare for the next day and the next event. The next pillar is the context-modulated computation, and that means that we're learning new behavior and new function all the time, but as we learn them, they're not rigid. They're actually modulatable. So what do I mean? Let's say that I want to encourage a toddler. So it will be more something like, that is very good, yeah, I'm so proud of you. And just think that this toddler became, after a teenager, I think you're better off express yourself with something like. So if we had to think about any encouragement pattern as a different function, it would be very inefficient. So this context modulation allows us to learn only what we need and modulate as we go. And the last one is the new behaviors. And the new behaviors is the accumulation of everything together when through internal exploration, we also do safety and security to predict the future. And with all this together, we're able to get our experience, our internal studies, and be prepared for things that we never saw before. This is what we call lifelong learning. So let me share with you some of the great results. So the first of them is about continual learning. And here I want just to mention a particular problem that we have in current AI. So let's say that you trained your system on 1 billion examples. Let's say these examples were related to driving on a road. And then your car made an accident, and because of that, you want to give the new 30 examples and train the system on that so that you will not do exactly the same example. You cannot do that, because in the state-of-the-art neural network, what's happened is if you take the new 30 examples and retrain your network again, you're actually writing in the same location in memory where the previous examples set, where the previous 1 billion examples set. And that's why you cannot train on one and then train on other. That is what we called catastrophic forgetting. So this is the current AI, and we would like to have something much better. So what people are doing nowadays in AI, when they found something that they really need to train the system on, they take the new 30, the 1 billion early one, they're putting them together as a new training set, stop the system, and restart doing it all. In the AlphaGo, it took 9 months to retrain the system. If you have a self-driving car, it will be probably more than 10 months. So if it goes to critical operation, it will be something like that. Oops, wait, don't move, I'll be back in 11 months, and I'll show you. So that's the notion of what we would like to do with the continual learning. So replay is something that happens in biology. And Irvine noticed that in biology, we don't have actually an option of retraining because the examples from yesterday are no longer here. The only option that we have is to replay the internal representation that we have in the brain that tell us something about the previous thing that we saw. So they tell us another thing, that in biology, we're not going to replay everything from childhood till now, but we're only going to replay this particular memory that are in risk of being forgotten when the new memories are being put in. Baylor School of Medicine showed us another thing, that for practical reason, instead of replaying the internal representation, they take the internal representation, they regenerate input-like information, kind of like what we do in dream, and then take this input-like information that was regenerated from the internal representation and replay it to the system. And this way you get the best results. It also gives very nice interpretation and functional explanation of dreams. Internal explorations. So Columbia University showed how an arm of a robot can learn its own structure and function by internally playing with the ghost arm. And this way, if later on the arm is injured or has other changes, the arm will be very fast able to adapt to a new condition. NYU showed us that in order to understand better, you can do self-quizzing. So what is self-quizzing? You can take image that you got, maybe even an unlabeled image, and take a small piece out, and then ask yourself, what's the piece that is missing here? So you know the answer because you have the full image. So in that way, you created a labeled question from an unlabeled image. You can go ahead and take the colors off and say what was supposed to be the color. Again, you know the answer. You can do something that is even much greater. You can take from one large scene, an image, you can take small part of the image, and say which of the other small images are part of the same scene. This way, you can learn, for example, about the connection of train and the train station building, because they were in the same situation. So notice that this is actually bringing you to another different understanding of AI. Instead of having a pure pattern recognition, you start having correlation, which is really the step of what brings understanding. Context-modulated computation, University of Chicago taught us that the brain is changing its own circuitry totally based on the context. For example, a hungry rat will compute with a different architecture than a satiated rat, because there are some top-down connections that are there only when the rat is hungry. This way, the prefrontal cortex will start leading to different kinds of neurotransmitters. Wyoming took this notion of neuromodulation and translated them to better machine learning. They showed that you get far higher capacity, and also you can switch seamlessly between different tasks. UPenn took it further and showed that even in strategic games, if you consider the task something like get blue then red, or get red then blue as the context, then you can modulate your computation very fast and have a different behavior in an environment is just modulation in a much more efficient way and much more optimal way. Tufts University, they studied the mechanism that allow lower animal to regenerate after amputation and to have their neural system regenerate after they put a new eye into the system. And in this way, they look at flexible robotics, and it has some reason to escape from where it is, and they allow this flexible robot to change its shape and to, in fact, grow a leg so that we're able to do the functionality that it needs. University of Massachusetts showed us that because you can associate different things and have better association and understanding between things, you can actually have searches which are much more intelligent. So if you go into a home, you've never been there, and you ask to look for a kettle, you look around, you're going directly to the room where you see the refrigerator there and not to the bedroom. And as you get to the kitchen, you go directly towards the stove, and there you're likely to find the kettle. SRI prepared it for us an interesting evaluation testbed that is built on StarCraft 2. So what they did is they enable the program to have a ghost programmer that will be in the back and change all the time the situation. So when you're a player, you must be all the time aware, because you're going to be in situations you've never been before. So one thing that they showed us is that they can changes in the terrains, and they also can make changes and alter the unit capability itself. But they go on and makes it even harder, so that friends can switch into foes, and you can even increase the weapon range. So you cannot play this game unless you have lifelong learning AI, and that's why we can use it as a testbed. And now I would like to change gears and talk about another problem that is plaguing current AI. So it was shown that AI can get really confused, and if you add some kind of perturbation, it will recognize the panda on the right as a gibbon. Even that we will not see any type of difference, the machine learning will already see it as something totally different. So this is what we call adversarial AI, and it was shown that it's very easy, in fact, to come up with this perturbation. You can do it in an extremely fast algorithm. So the question that comes, is this kind of trick works only for still images? So Intel showed us that this is not the case, and I'm going to show you some example of physical attack, and in the background you will hear some clicking. This will be a Geiger count sound that will be higher when the deception, when the attack is successful. So let's start. So this is a face recognition system that's recognizing Chen, a graduate student in Georgia Tech. Now he puts these well-designed classes, and it makes him look like Brad Pitt. I never knew how easy it is to become Brad Pitt. Then they're looking at a speed limit. It's 15, but this speed limit is going to look like 65 just after you put some sticker on the top of it, which is a great excuse to tell a policeman when stop you speeding. And if you can see there are 2 stop signs there at the end, the machine will recognize one of them consistently as a person. So if you want to go further, it's not only still images or video, but we can go to other type of modalities. So a system that will can transcribe something that doesn't work to say without the database, the article is useless. And if you add a little bit of noise and bring it again, then the system will tell you something that is totally different. It hears the same. It will transcribe something pretty scary, like, OK, Google, browse to evil.com. So this can happen in different ways, and it sounds like the sound doesn't work here, so it's OK. I will hear myself better. There is another type of attack which is called a backdoor, which is really cool. It's so easy you can do it yourself. So let's say that there is a club, it's a restricted club, it's closed for average human being. Only Wonder Women, Wonder people can get into the club. So let's say that this average man wants to come into the club. So what does he do? He chooses some type of accessory. He takes this accessory, it can be a hairpin, it can be a necklace, and it injects it into pictures of Wonder Woman in different sizes or in different angle. Then he blurs this adding on, so for the eyes it will not look that strong, but for the AI club it will be enough confusing. It will add it to the training set in order to poison the system, and now this average person will come, will put on the glasses, and voila, the system recognizes him as Wonder Woman and will let him in. This is a very easy way to do. So, are deception attacks relevant to the DoD? Well, if our enemy would design some kind of sticker that will let our eye think that it's another kind of vehicle, it can be a little confusing, or the enemy could use all kinds of other attacks that I described. So one thing that is standing for us not to worry so much is that all current physical attacks were designed with full knowledge of the system that attack. In fact, they needed the copy of the AI to be with them because they needed to look at every single weight. However, there is the other side, that the field of attacks growing very fast. In fact, you all know that image recognition worked so well almost to 100%, but you can attack all these image recognizers so that they recognize images with almost 0%. So the field of adversarial AI started coming with defenses. However, for every defense that was suggested up till date, a new attack that came undid it totally. So the feeling today in the field is that it's much easier to design an attack than to come up with defenses that will be strong, so that the design of attacks outpace defenses much greatly. What can we do? DARPA comes to the rescue. So that's why we now form a new program that is called GARD, Guaranteeing AI Robustness Against Deception. We start with asking fundamental theoretical question: why is AI so brittle? What features will make the system stronger, more robust against adversarial attack, and what features will be such that they will not really be helpful? And this fundamental theory is the basis for the new type of defenses that will come. The second one is coming with these principal defenses in order to have very strong system. So I want you to notice the previous defenses that were suggested were coming against a particular attack. But for analogy, think about defense system. The defense system is there to protect your body, period. It's not really helpful if you had some kind of immune system that was good against the flu from 2008. And so that's the type of principal defenses we're talking about. And the type of defenses we're talking about will not only work for classifiers, even that's the example I was talking about, but they will in fact be working on any kinds of AI localization of an object, prediction, decision-making, reinforcement learning, strategy making, you name it, because in its base, the deception comes for one reason, and the defense will have to sit in that place. For the third part, we'll come with a test bed to evaluate if systems are defensible. We'll do it relatively to a scenario. What do I mean by scenario? It will have to tell us how much time the attacker has, what computation time, what knowledge it has about the system, what the defender has, what the defender knows about the attacker. Does he have enough time to detect if there are attacks, or he has to work without knowledge? All these type of things will come into the scenario, so that once we have this test bed, we'll be able both to defend the system and to say when we can use it safely. And with this, I would like to close my talk. And I want to say that, and it seems like in the upcoming future, both if we talk about robotic arms, or if we're talking about smart prosthesis, or some other type of AI embedded in the world, we would like this AI to come partially trained from the factory, being able to be trained more by the owner, and even then remain adaptable, aware, and resilient. And I would just predict that in future years, what we call today AI, or much of what we call AI, would be called pattern recognition algorithms. And in order for system to qualify as an AI system, that will have to have lifelong learning and robustness. And with this, I thank you very much for your interest. And if you're interested in pushing AI to be your resilient, reliable partner, please contact me. Here, I'll be here until the end of the day. Thank you very much. Okay, I got a bunch of interesting questions. Let me just look at the time. Okay. So one question is, are you looking at how the model can change, like depth of a neural network or type of neural network? How do you transition an existing network to a new one? So that's what we do in this project. We're looking at, if I mention neuromodulation, it means that we're not looking at neurons as only transferring electrical information, but they also transfer chemical information. And when you have these two, it's both richer, and you can understand how you can much more easily change your network. So it's not necessarily open and closed. You can flow into some chemical, and the whole thing will feel differently. Another question. Okay, so this question is about the capability of the network, of the system. Do we get greater capability in general for the system? Are we able to do more behavior, or are we just able to do this change of behavior faster? So I like this question, and the answer is we actually can do things that are much stronger. So if I want kind of to say the theoretical background, the AI of today is based on what we call the Turing machine type. So the Turing machine is what Alan Turing started in the 1930s. And it's the notion that you have to bring a program and to put it onto a computer. And the computer is worth nothing without it. It has no initiative, it has no direction. But once you put a program, it will do exactly what your program wants. And that's why the program is fixed. There is another theory that we call it super Turing that was invented since the 90s, and still people are working on it now. And super Turing actually describes this machinery where you can all the time change and adapt. So it doesn't have to be a fixed program. And our program, Lifelong Learning Machine, is based on the super Turing theory. And there are various theorems and counting arguments that people published in the last 4 years that show that if you look at what all the Turing machines can do, let's say you call it Aleph, and you look at all the things that lifelong learning or super Turing machines can do, it actually can do 2 to the Aleph. So it means it actually do exponentially more type of behavior than the previous one. So if we think about computer, and then perhaps super Turing, and then perhaps humans, so super Turing is much stronger than Turing, and that's why actually in lifelong learning we'll get not only much faster adaptation to the world, but actually many more possible type of behaviors. Okay, I'm done. Thank you very much.